Hello, we are going to discuss a fourth case study in the course today, and this lecture is about a compliant mechanism used for tissue cutting, and the new feature that compliant mechanism offers here is a way of passively limiting the cutting force of the device. So, we look at how a compliant mechanism can be used in applications where you want to cut tissue safely by putting an upper limit on the cutting force. Okay. So, we have now a compliant device that has a built-in sensitivity to the stiffness of the tissue. When we say stiffness, it is also related to the cutting force. We can say stiffness or strength also. So, stiffness, or we can think of this as strength. Okay. So, we look at how we can do it using again compliant design. That is what we illustrate in this case study. The key reference for this is this paper that appeared in Journal of Medical Devices. So, compliant mechanisms have a number of biomedical applications. This is one of the examples, volume 6 in 2012. As you can see, this also has other features, which is other than passively limiting the force, that is one feature. Okay. This is a safety feature. So, we have a device that ensures that when you are cutting something, it could be tissue or something else, that it will not apply force more than some value that we set. So, the mechanism is designed for that purpose. So, other feature is this teleoperated tissue cutting, that is you have master slave mode. So, whenever you do teleoperation for cutting purposes, you need to have a way of sensing forces. So, here the compliant mechanism is also used for sensing forces. So, there are two features, one is an upper threshold on the cutting force, other is sensing of forces. This is a setup that we have developed. So, here is compliant end effector, and there is some phantom tissue. We did not really go for real tissue, it is a phantom tissue that we can make ourselves, and there is a master here, that is my student applying displacement to move something, and the slave device here which cuts the tissue. So, in between we can say there is a geographical divide, even though it is in the same lab, it could be one location in the world, there could be another location, and these two are connected through the internet. So, when holding the haptic robot here, what you have is a haptic robot is there. This is a phantom device, haptic robot. The movement of the hand here is communicated to the slave device, and the slave device moves. As the slave device moves, the cutting force on the phantom tissue is measured, and that goes here. So, what goes from here to here, if we say the input from here to here is going to be the position information. So, the motion of the hand is related to the slave device, and then from this to the user comes the force feedback. So, it is a closed loop system, teleoperation, you can cut something while sensing the force. So, that is normally done, that is not anything new. What is new in what I am going to talk about is this cutting force is limited passively, not by control, limited passively to a certain value, so that you can cut things that take less than certain value of the force, other things it just would not cut, it retracts by itself. So, there is a built-in kind of intelligence in the device that will make you safely cut something with only that much force. The device that we have has a cutting force about 2 newtons, more than that it would not cut, it simply comes back by itself, there is no control. So, a good design usually tries to eliminate the need for control, and here is an example of a design which has passive control built into it, not active control where you have a controller and an actuator, a control input and all that. Do not have all this, just normal device that ensures this safety by using a compliant mechanism. So, here is again the compliant end effector is indicated, compliant end effector. So, the compliant end effector that we have is encased in this box here. So, you do not see much of that, you will have to see later. What you see here is a scalpel. So, there is a little sharp thing here, that is what is going to cut the tissue, that is attached to a compliant mechanism that we will discuss, and there is a camera, a CMOS camera that looks at the displacement of this scalpel, and based on that we estimate the force, and knowing the force the user can cut or not the teleoperation, but more than that there is an upper threshold on this. When the force of cutting force exceeds that value, the scalpel will simply retract. Okay. So, imagine that there is a cutting blade, you are cutting and it could be teleoperation or otherwise. If you hold to this compliant mechanism where the scalpel attached as you are cutting, when the force of cutting exceeds certain value, it simply will retract. So, if the specimen is here, it will simply will retract, that is what we will see here. So, here is the end effector of the thing. So, the specimen to be cut is here, the scalpel is attached to the compliant mechanism. This is the knife edge that cuts here. So, we have the compliant mechanism and there is a camera looking at this point. So, as the compliant mechanism, as this whole casing is moved, this acrylic casing in which the mechanism enclosed is moved, this is the direction of cutting. When you are cutting, there will be some force, because of the force applied here or felt over here, okay, this point will move. So, this will be the input here and this will be the output. Okay. So, this movement is seen through this camera and there is a computational model of the compliant mechanism from which we know the force applied over here. So, we have modeled the mechanism, if you know the displacement here and here, or just the camera is looking at this displacement, we can estimate what the force is. Once you know the force, you can do the teleoperation by giving force feedback to the user who is at a remote location. Another thing, this mechanism has the interesting feature that when the cutting force exceeds certain value here, here is where we have the cutting taking place, then it will automatically retract. The retraction that I talked about happens here. Okay, that is the compliant end effector's novelty here. So, here is the thing, when I have input force, this input force in this direction, because the scalpel will be attached to this, okay, this is the scalpel that you are cutting, right, that is the scalpel. Now, when you move it like this by applying force, this point will move in that direction. Earlier we had seen that when there is a force in this direction, we see that output is here. So, we have an input here, then what will happen is this point will move up and this point will move down. Earlier we had seen that if I apply input force this way, this will come down. So, let us look at this in a device. So, here is the thing we are talking about. So, let me actually put it like this. So, now when there is cutting force, so this way, so I apply the force, you can see this coming down. So, this point comes down. By how much it comes down, we can estimate what the force is here. Okay, that is a force sensing principle. At the same time, when I do this, this also moves a little bit up. That is probably hard to see here, but this point actually when you do this, it actually moves up here. So, what happens is that when cutting force exceeds certain value, this actually retracts automatically. Okay. So, that is what is shown in the simulation over here, that when you apply the input force in this direction, it is actually moving up. So, this is called the output 2, this is the second output, this is the first output. So, this is used for force sensing indirectly. So, we sense the displacement and then hence the force. This output 2 helps in retraction. So, when you apply a lot of force here, then it would move a lot. Imagine that the whole thing where it is attached to some frame, this whole mechanism is moving, let us say like this, to cut some tissue here. So, here is where let us say some tissue is there, you are just moving the whole thing, it is going to cut. As and when the force, in this case when it cuts like this, force will be other direction. So, it probably makes sense with what we have now indicated here. So, let us say that the scalpel is like this, and we have the specimen to be cut over here. The specimen is here, when this moves like that, cutting force of course will come like that, that will make it go up. So, depth of cut will change a little bit depending on the stiffness. Okay. And when the force exceeds certain value, then this displacement from of the scalpel, this output 2 will be so much that it will not cut anymore. That is the idea. So, on the one hand we are able to sense force, on the other hand we are able to retract when cutting force exceeds certain value for which we design the mechanism. So, that is what the compliant mechanism is doing here. For which to design, we had looked at this spring lever model that we have already discussed, spring lever model, SL model. So, if you look at this thing here, the input is here, there is some input side stiffness KCI. So, when there is force like that, this is the force input or input force, then two things happen. One is that this point moves like this to indicate the displacement and to indicate the force directly. At the same time, this point actually moves up as it is shown. So, retraction. So, there is a knife edge that retracts without cutting. So, we can make this model. There are leverage ratios, 2 of them now, and there are 2 output side stiffness. Earlier we had taken single input single output spring lever model where you had KCI, KCO and N, but now we have KCI 1 input and then KCO 1, KCO 2 and there is N1 and N2 leverage ratios. Okay. So, that is how this model was built, so that we can design for a particular cutting force. Here are the details of the mechanism, all dimensions are in millimeters. So, the blade is here, so which is shown over there. So, that is the blade attached to the mechanism, and these are going to be attached to a carriage, the whole thing will be moved to cut. So, this is like now what we call the compliant end effector for the cutting tool. So, cutting tool, the scalpel is here, and this is the end effector. Like a robot end effector, we have now a compliant mechanism end effector. So, and the dimensions is 97.3 millimeters and so forth. It's a big device made of this material here is polypropylene. This has Young's modulus about 1.5 gigapascals, roughly what we had found, okay, polypropylene. And here is how it works. When you are, the specimen is here and when you are moving it there, cutting force will be in this direction on the mechanism. So, the cutting tool once again is here. What will happen is, when the cutting force exceeds at some point, you see how the nonlinear deformation has taken place, it has moved here, it retracted. So, as you are doing, because of force it just goes. So, since if we are still moving this casing, this is the casing to which the mechanism is attached, casing to which the mechanism is attached, mechanism is attached, it keeps going, but then this is retracting. So, what will happen is this scalpel, when the cutting force exceeds, will simply ride on top of it, or sometimes it may even go back. Okay. So, it just goes like this without cutting. That means that we are ensuring that cutting force beyond certain value is not even applied on the specimen. So, that is the thing, rigid body translation of the casing will basically ride over it. Okay. That is how it works. So, there is a cutting force Fc threshold put on the mechanism. Once again, output displacement here is going to indicate how much cutting force is there. This is the working principle of the device. In order to do this, we had to pre-calculate certain values about the effect of the depth of cut. So, when you have the mechanism, if you take depth of cut at D1, D2, D3, D4, that is how much of the scalpel is inside the tissue. Let us say if it is D3, that means that the tissue is up to that D3, D4 means up to that, D1 means just barely touching, D2 is little bit inside. So, this indicates the depth of cut. For a force Fc applied at different depths of cut, what we have shown here is the force at the input versus the y displacement. So, y displacement here is in this direction, that is y, and this is x. Okay. So, what we have here, y displacement goes like this. It does not depend so much on the depth of cut, because when I zoom in this portion over here into this, then I see that there is a little difference, but otherwise for all depths of cut the y displacement is the same, whereas x displacement there is difference. So, the x displacement for depth of cut 1, the red line, and then black dashed line, blue dotted line, and magenta dot dash line. So, they are slightly different in terms of the x, that is how much it moves in this direction. X is this way, y is that way. Y is the retraction, that is what you are interested, and that does not depend so much on the depth of cut. By knowing the x displacement, we can see what the cutting force is at any point. So, we do not actually, we are not measuring displacement here, we are measuring at some other point and the mechanism as we explained in the previous slides. So, if we know the displacement, let us say I have displacement some value here, then I would know depending on the depth of cut, then I would know what force it is. Okay. So, that is how it is going to work in terms of the force sensing as well as limiting. Limiting is that you see, if you have a depth of cut of D1, then the curve goes all the way here, and then at that point it comes back. The reason it does is that by that time the y displacement has exceeded some 2.5 input displacement is there, y displacement is nearly 7 millimeter. This is meters, here you may not see, this says 10 power minus 3. So, meaning that it is in millimeters, nearly about 7 millimeters y. If the force is 2.5 newtons with the depth of cut D1, I have already retracted. If it is depth of cut is D2, about 5 millimeters, because that is when it comes down like this, and this is 3 and this is about 1 for D3 and D4 depth of cuts. So, based on the depth of cut and the force, we see when it retracts. So, this a priori analysis enables us to estimate this without having to go to finite element analysis, which in this case is very non-linear. We do not need to do that because we want to do it in real time. So, based on this model, when we have an experiment where there are different cutting forces required for an inhomogeneous specimen. So, here is a specimen that was actually simulated and also made experimentally. So, there is this gray one that requires half a Newton cutting force, and then this black one requires 1.8 newtons, and then this darker grey one requires 1 Newton. So, as you bring the scalpel, which is where it is, as you bring the scalpel and start cutting, so you can see that it was slowly increasing the force, and then it suddenly jumps because it has to go to a higher one, and then comes back to over here to cut about 1.8 newtons, and then comes back and cuts the 1 Newton, and then goes. The way you are cutting, it just shows how y and x displacements change for various depths of cut here, and we can see for each force how it is doing it. So, here we are showing experimental measurement, and then estimated using this a priori curves, and then direct simulation that was done later to see how they go. Obviously, experiment, which is this dashed line, differs slightly because there are a lot of uncertainties in the experiment, but the actual full simulation and estimated using the a priori curves, they match quite well. So, we also did calibration using a load cell, so that when the scalpel is moving, how much force is there. So, there is a calibration data points for a particular thing that we want to cut. So, we will know how it varies. Okay. So, we have the calibration done by comparing with a load cell of cutting some specimen. So, which had a force varying as shown in this case. So, we made a specimen that has cutting force required 0.5 newtons and 2 newtons, FC1 and then FC2. So, that means that this is a little stiffer or stronger, either way, stiffer or stronger part compared to this light one. When we are cutting, how it would go at different depths of cut is what we can use the model and verify. So, here is the thing where we have a gelatin based a hydrogel, which is very flexible or soft, and then we have PDMS, which is also soft, but relative to this hydrogel it is stiff. So, when you cut along this, so we are done in a way that if you cut with a rigid end effector, if you just take a scalpel and go, you will cut hydrogel, you will also cut PDMS. So, we will cut through the whole thing. Whereas, if you cut with our compliant end effector, that is a blue curve, it will not go beyond this 2 newtons. We have 2 newtons the way it is designed. So, it will cut through the gelatin, and then it would not cut to this rest of the portion. It will just cut here and then skip over and then start cutting later. It will ride over it, as you will see in a video. So, here is the experiment, the cutting force. So, when you go to the hydrogel, it is going to some 2 newtons. The moment PDMS is encountered, it just stays there 2 newtons. So, it will just go there, it will not be able to cut if PDMS requires more force. There is a momentary slip that happened in the experiment, but that can be ignored, but the fact is that there is a passively limited upper threshold on the force. This was information flow when you do teleoperation. So, we said at the beginning that you can also do teleoperation. Now that we have a safe device which cannot exert more force than needed. So, whenever you have a master slave operation, for a patient is always little bit troublesome to see that a robot or a automated device is cutting. What if it exerts more force at places where it is not? Now, we have an end effector that limits the cutting force. So, it is more amenable for this master slave operations or teleoperation. So, that you do not have to worry that it is going to exert more force than certain value, and the force can be decided by the design of the compliant mechanism. So, for that information flow there is user's position is related through haptic device to a master computer, and through LAN it goes to the slave computer and goes to the finally compliant end effector. Now, the force there comes visual feedback, and then the computation, the force comes to the again master computer through haptic device to the user. So, both ways there is information flow from master, in this case human, and the tool which is a slave. Machines are always slaves to humans. So, that is what we have here, the information flow. So, to summarize, in this particular device what we have done is developed a compliant end effector whose two features of sensing forces and limiting the cutting force are demonstrated. So, we demonstrated that passively can limit the cutting force. So, here we have less strong or weak material can be cut easily, and the strong material comes, it will just retract. So, let us look at the video and come back to this here. So, let us look at this video. So, we can see the compliant mechanism. We can say scalpel and move the stylus. Master, the slave would be the cutting tool actually cutting. So, we can see how the cutting tool is moving, where it will lift off when the thing comes. So, let us watch this, and I will be showing another movie where it will actually lift off. This is the master, and then the slave we saw the other end. This was before touch screen days. Yeah, so it was just screen and then you move it and that will go to the slave. So, let us look at this lift off operation. This is the stiff PDMS, it rides over it. When it comes to the hydrogel portion, it will just cut it. So, now the scalpel is up there, not actually cutting, it is just riding over it, and then when it comes to the flexible part, it will just dip in. Yes, so it went to that and started cutting along this profile. So, the stiff one or strong one it is not cut, flexible one is happily cut. So, this compliant mechanism, the retraction feature is used in this particular device. So, let us look at the main points, that the compliant end effector is useful because it has built in safety feature, and we also have developed a priori analysis, more details you can look at in the paper, where there is prediction of the cutting profile also because of this x and y displacements of the input point that we pre-calculate using finite element analysis and fit the curves at different depths of cut. That not only tells us how to estimate the force, but also estimate the cutting profile once you know the stiffness of the workpiece. So, a compliant mechanism can be used in applications where rigid ones will not be suitable. There you would need a sensor, a controller, whereas this one can automatically go, which is what people find in many biological organisms, whether it is walking or flying. Compliance is used effectively to passively change things. So, when an insect is flapping wings, people say that insect is not doing this figure 8 motion of the tip to twist, it is actually going like this, but the compliance in it is actually giving it the slight twist that it needs. Similarly, walking, when obstacle is encountered, if you have a robot, then you have to have a controller to avoid the obstacle and go, whereas if there is compliance, it will simply move away from the obstacle by bending or deforming and then moving on. So, we had shown one video of a robot with compliant legs several lectures ago. That is where the compliant design actually helps. If you use compliant design effectively, you can reduce reliance on control, you can avoid having to control something which nature seems to do extensively. Thank you.